Right now, without you feeling a single thing, you are moving at over 1600 kilometers per hour. That's how fast the surface of the Earth spins at the equator. You don't feel it because everything around you, the air, the ocean, the ground, your own body, is moving at exactly the same speed in perfect sync all the time. Now imagine that stops. Not slows down. Stops completely. For just 5 seconds. Then starts again exactly as it was. 5 seconds doesn't sound like much. You've spent longer than that reading this sentence. But in those 5 seconds, everything that wasn't bolted down to the planet, the atmosphere, the oceans, every person standing outside, every plane in the sky, would keep moving at the old speed while the ground beneath it suddenly wasn't. The result wouldn't just be an inconvenience. It would be one of the most violent, planet-wide events in human history, compressed into less time than it takes to tie your shoes. Let's break down, second by second, exactly what would happen. To understand why stopping the Earth would be catastrophic, you first need to understand why spinning at 1600 kilometers per hour feels like nothing at all. The answer is inertia, the same principle that keeps a cup of coffee sitting still on the tray table of a smoothly cruising airplane, even though the plane itself is moving at hundreds of kilometers per hour. As long as speed stays constant, everything inside that moving system, plane, coffee, tray, you, moves together and nothing feels off. Earth works the same way, just on a planetary scale. The ground, the oceans, the atmosphere, and every living thing on the surface are all spinning together at the same speed all the time. There's no friction between you and the moving planet because you're not sliding across it, you're rotating with it. This speed isn't the same everywhere either. At the equator, the surface moves at that blistering 1600 kilometers per hour. Closer to the poles, the speed drops dramatically because you're rotating around a much smaller circle. At the poles themselves, rotational speed is essentially zero. That detail matters because it means a sudden stop wouldn't hit every part of the planet the same way. The equator would experience the most violent effects. The poles would barely notice a thing. Now picture the moment it actually happens. The planet's rotation halts instantly, somehow, for the sake of this thought experiment, but nothing riding on top of it slows down at all. Every person standing outside at the equator is suddenly moving at 1600 kilometers per hour relative to the ground beneath them, which is now stationary. That's roughly the cruising speed of a commercial jet. There is no surviving that kind of instantaneous deceleration. Anyone not literally anchored to the ground would be thrown violently in the direction the Earth used to be spinning, an unsurvivable planet-wide event within the first fraction of a second. Buildings fare only slightly better, and only because they're physically anchored into bedrock. Even so, the sudden shift in forces acting on their foundations would put stress on structures never designed for anything like this. Loose objects, cars, furniture, anything not bolted down, would be hurled sideways with the force of a high-speed car crash. Nearer the poles, where rotational speed is much lower, the effect is far gentler. Someone standing near the Arctic or Antarctic Circle might feel barely more than a strong gust of wind. This isn't a uniform apocalypse. It's a violent, physics-driven event whose intensity depends entirely on your latitude. And that's before we even get to the atmosphere and the oceans, which are about to become the real main event. The atmosphere is a fluid, and fluids don't stop just because the ground beneath them does. All that air, previously spinning along with the planet at up to 1600 kilometers per hour, would suddenly find itself moving relative to a now stationary surface. In practical terms, that means winds erupting instantly at supersonic adjacent speeds, dramatically faster and more violent than the strongest hurricane or tornado ever recorded. These aren't localized storms. This is a planet-wide wind event, hitting hardest at the equator and tapering off toward the poles, exactly like the ground-level effects we just talked about. Trees wouldn't just bend, they'd be stripped bare or uprooted entirely. Loose structures, vehicles, and anything not deeply anchored would be swept away. Dust, sand, and debris kicked up by these winds would fill the sky almost instantly, turning daylight hazy or dark in a matter of moments. Visibility would collapse across huge portions of the globe. And this is happening in just 5 seconds, the exact window this thought experiment gives us before rotation resumes. Even after the planet starts spinning again, that air doesn't just calm down instantly. Those wind patterns and the destruction they cause would continue playing out for hours or days afterward, long after the initial 5-second event technically ended. If the atmosphere going haywire sounds bad, the oceans are about to make it look tame. Water, like air, is a fluid, and it too keeps moving at its old rotational speed the instant the ground beneath it stops. Except water is far denser and heavier than air, which means the forces involved are almost incomprehensibly larger. The result would be mega-tsunamis, generated simultaneously across every ocean on the planet, triggered not by an earthquake or a landslide, but by the entire body of water suddenly sliding relative to the seafloor beneath it. Some estimates for an event at this scale suggest waves that could reach kilometers in height near the equator, dwarfing any tsunami in recorded history by orders of magnitude. Coastal regions near the equator would be hit hardest and fastest, with almost no warning time, since the trigger event and the wave arrival would happen almost simultaneously. Low-lying coastal cities across South America, Africa, and Southeast Asia would face the most extreme versions of this effect. Even away from coastlines, the sheer redistribution of ocean water, sloshing violently across ocean basins in the minutes and hours following the event, would reshape shorelines, flood inland regions, and disrupt ocean currents for a long time afterward. Cities face a two-front assault. The initial violent deceleration, followed immediately by hurricane-force winds and, in coastal areas, incoming mega-tsunamis. Skyscrapers, built to sway slightly in normal wind and resist earthquakes to a certain degree, were never engineered for a sudden, planet-wide inertial shock combined with sustained supersonic winds. Structural failures would be widespread, especially in taller buildings where the upper floors experience even greater relative motion than the ground below them. Bridges, particularly long suspension bridges, would be especially vulnerable, their long spans acting like sails against the sudden atmospheric onslaught. Power infrastructure, transmission towers, substations, underground cable systems, would suffer catastrophic, near-simultaneous failures across entire continents, triggering blackouts on a scale humanity has genuinely never experienced. Underground infrastructure fares somewhat better, protected from wind and initial impact by the ground itself, though subway tunnels near coastlines would face their own flooding risks from tsunami surge. In the immediate aftermath, cities that survive structurally intact would still face days or weeks without power, clean water, or functioning transportation, essentially thrown back to a pre-industrial state overnight, in the middle of the largest natural disaster in recorded history. Let's be direct about the human cost, because it's the part of this scenario that's hardest to soften. Anyone outdoors and unsheltered near the equator during the initial event faces almost certain death, thrown at speeds comparable to a plane crash the moment the ground stops beneath them. This isn't a survivable scenario through preparation or bracing. The physics simply don't allow for it at that latitude. Indoors, especially in reinforced buildings away from windows, the odds improve dramatically, though falling debris, structural damage, and the secondary effects of extreme wind still pose serious danger. People in vehicles would face chaotic, often fatal outcomes, as cars are thrown and tumbled by the same forces acting on the ground beneath their wheels. The closer to the pole someone is, the better their odds. In much of Canada, northern Europe, or southern Chile and Argentina, the direct effects would be far less severe. Strong winds and disruption, certainly, but nothing on the scale of what the equatorial regions would face. In the hours and days afterward, survivors everywhere would face a second wave of danger. Collapsed infrastructure, contaminated water, no electricity, and overwhelmed emergency services trying to respond to a disaster that hit every single country on Earth at exactly the same moment. At any given moment, there are roughly 10,000 aircraft in the sky above us, and every single one of them is about to have a very bad 5 seconds. Aircraft in flight are already moving relative to the air around them, using that airflow over their wings to generate lift. When the ground suddenly stops but the atmosphere around a plane keeps moving at the old rotational speed, that aircraft is instantly hit by relative wind shifts far beyond anything any aircraft is designed to handle. Depending on location and heading, planes could face sudden, extreme changes in airspeed, violent turbulence, and potentially catastrophic structural stress, especially planes flying near the equator, where the speed differential is most extreme. Even well away from the equator, the sudden atmospheric chaos would make controlled flight incredibly difficult, if not impossible, for at least several minutes. Air traffic control systems, satellite navigation, and communication networks would likely be disrupted simultaneously, leaving pilots with limited information and extremely limited time to respond to a crisis that, from their perspective, would come with absolutely no warning at all. It's one of the more sobering parts of this scenario. At the exact moment the ground-level disaster begins, thousands of aircraft carrying hundreds of thousands of passengers would be caught in the middle of it, entirely without warning. Interestingly, not everything tied to Earth would be affected the same way, because satellites don't rely on the ground spinning to stay in motion. Objects in orbit are governed by orbital mechanics, not surface rotation. A satellite circling the planet would, for the most part, continue on its existing trajectory largely undisturbed by a sudden change in how fast the ground below is turning. The International Space Station and GPS satellites would likely continue operating in orbit without any direct physical effect from the event itself. That said, the consequences on the ground would still reach them indirectly. Ground-based control stations, tracking systems, and communication relays, all vulnerable to the same blackouts and infrastructure failures happening below, could easily lose contact with orbiting spacecraft for hours or days, even if the spacecraft themselves remained perfectly intact. It's a strange contrast to hold in your head. Astronauts in orbit watching a genuinely planet-altering event unfold beneath them, largely safe from the immediate physical forces tearing through the surface, but potentially cut off from any communication with the chaos happening below. Before we look at the aftermath, it's worth pausing on an important point. This could not actually happen through any natural process we know of. Earth's rotation carries an enormous amount of angular momentum, physics term for how much spinning force is baked into a rotating object. Stopping that instantly would require an outside force so extreme it's genuinely difficult to describe in real-world terms. It's well beyond anything an asteroid impact, a solar event, or any natural phenomenon we're aware of could realistically produce. Earth's rotation does change, but gradually. Tidal friction from the moon is actually slowing our planet down by a tiny fraction of a second every century, and even that barely noticeable drift takes millions of years to add up to anything significant. So why bother imagining an impossible instant stop? Because thought experiments like this one aren't really about predicting the future, they're about making invisible physics visible. Most people never think about the fact that they're moving at 1,600 kilometers per hour right now. Scenarios like this are one of the only ways to actually feel how much hidden motion and energy is quietly built into the ordinary experience of just standing still on Earth. Now, the strange part. After 5 seconds in this thought experiment, the planet resumes its normal rotation at its normal speed, as if nothing happened. But the damage done in those 5 seconds doesn't reset along with it. The mega-tsunamis triggered by the initial event are still racing across ocean basins, hours away from finishing their destruction on distant coastlines. The hurricane-force winds unleashed by the atmospheric shift don't just vanish. They continue raging, gradually dissipating over the following hours and days as the atmosphere slowly resynchronizes with the resumed rotation. Collapsed buildings stay collapsed. Damaged power grids stay damaged. The dead remain dead. 5 seconds of physics-breaking chaos would leave behind weeks, months, or even years of recovery, cleanup, and rebuilding. A scale of aftermath closer to a global war than a single natural disaster. There's also a subtler, longer-term question scientists would likely spend years untangling. Does the atmosphere and ocean fully catch up to the resumed rotation cleanly, or does an event like this leave permanent, lingering changes in global wind patterns, ocean currents, or even the exact length of an Earth day going forward? In a scenario this extreme, even the smallest lingering irregularity could reshape climate patterns for generations. In the weeks following an event like this, humanity would be facing a genuinely unprecedented kind of global recovery, because for the first time in recorded history, every single country on Earth would be dealing with catastrophic damage simultaneously, with no unaffected regions left to send aid. Global supply chains, already fragile in the face of localized disasters, would face total disruption. Ports destroyed by tsunamis, airports grounded by structural damage, and power grids down across entire continents would make even basic humanitarian response dramatically slower and more difficult than after any disaster in real history. Agriculture would take a severe hit too. Flooded farmland near coastlines, wind-stripped crops inland, and disrupted supply chains threatening food security on a global scale for at least one full growing season, if not longer. Rebuilding codes and infrastructure standards would likely change forever, the same way earthquake-resistant construction became standard in vulnerable regions after major historical earthquakes. Coastal cities might reconsider decades of development in the highest risk zones. Redundancy in power grids and communication networks, treated as a nice-to-have before the event, would become an absolute non-negotiable afterward. Economically, the recovery would likely take years, possibly decades, given the sheer scale and simultaneity of the damage. There would be no unaffected wealthy nations to lean on for aid in the way disaster relief usually works. For the first time, the entire planet would be recovering from the same catastrophe at once. 5 seconds. That's all it would take. Not an asteroid. Not an alien invasion. Not a war. Just one quiet, invisible thing most of us never think about. The planet spinning steadily beneath our feet. Suddenly stopping and starting again, faster than you could finish reading this sentence out loud. It's a genuinely useful reminder of how much of daily life depends on things we never notice precisely because they never change. Gravity holding us down. The planet spinning smoothly beneath us. The atmosphere and oceans moving in perfect sync with the ground. None of it feels remarkable, right up until the moment you imagine it not being true anymore. This scenario will never actually happen. The physics required to stop a planet midspin simply don't exist in the natural world. But that's exactly what makes it such a powerful thought experiment. It's not really a story about disaster. It's a story about just how much invisible motion, energy, and precision is quietly holding the ordinary version of your day together every single second, without you ever having to think about it at all.